Okay. Hello everyone. Today I'm going to present a paper on efficient large-scale language modeling with mixture of expert. This paper shows how we can scale large language model more efficiently using mixture of expert layers. This paper is published in the ACL 2022. As we know that scaling up large language model has been one of the biggest attempts in recent years. Model like GPT-3, PLM, and Llama has shown remarkable performance in tasks like text generation, code generation, and reasoning. However, these improvements come at a significant cost. They require a huge amount of computation for training and inference. So this paper presents the mixture of expert, we can call it MOE, as a solution to this challenge. It also shows that MOE model can match or even outperformance than the regular density model while using finite computation resource. In this talk, I will cover the motivation of this work and the key idea of MOE models and the main research challenge explored in this paper. And first, we need to understand what is a large language model. Large language model is a deep neural networks trained on lots of text data sets to predict and generate text. They use the transformer architecture introduced in Attention is All You Need. It is a very famous paper. And this model can be fine-tuned for specific tasks. And also we can directly use this model, the model to predict using technique like zero shot or few shot. And the second thing we need to know is why scaling work. This is because empirical study shows that increasing model size and training data can lead to better performance across tasks. GPT-3 shows much stronger reasoning ability than smaller model like GPT-2. But here become a problem that scaling up model nearly increase computer cost, making training and inference much more expensive. Training model like GPT-3 requires thousands of GPT-4 works, and also inference is also expensive because every token active all parameters leading to a very high computation cost and emerging consumption. So this has motivated research into more efficient model architecture that provide benefits of large language model without much computer costs. And here are some existing method. We have technical like model pruning. We remove unnecessary connection after training, but this problem has some limitation. It requires retraining and it will reduce accuracy. And the second solution is quantization. This approach reduce precision to low memory usage. It is a trade-off between the efficiency and the performance. And the third method is knowledge distillation. We can also call it distill. It is to train a small student model learn from a large model's prediction. Their limitation is that the small student model may not generalize this as well. And the fourth architecture is what we will talk about today, the MOE. It uses sparse activation to scale efficiently, but it also we will introduce that the model is hard to train, and we may face some problem in fine tune. And so so between we introduce the MOE, we need to know what is the traditional dense model. The traditional dense models is a standard transformer-based large language model. All parameters are active for every input. This means every token processed by model activate all layers, leading to a very high computation cost. To solve this challenge, instead of using all parameters for every input, MOE model activates only a subset of parameters. For example, each input token is dynamically assigned to a small number of export layers, maybe 2 out of 1520 exports. And in this way, it allows the model to maintain a high capacity while reducing the computation cost for each input. And the key benefit of the MOE can be summarized as efficient scaling. It has a large scale, but without too much computer cost. And the second advantage is the improved generalization. Export can be specific in different layer of data. And the third advantage is lower inference cost. Only a fraction of model is used per token, and it's quite save time and save computation resource. And here are some comparison between the MOE and the dense model. And we can see for the parameter usage in the dense model, all they are active for every token, but in MOE, only a few export layer are activated. And for the computer cost, in dense model, it grows linear with model size. But in the MOE model, it grows sublinear. It reduces cost. And for the training scalability, the dense model is limited by for activation of parameters. But for MOE, it's more efficient to scale. And for the specializing, the dense model is trained for general purpose model. But in the MOE model, since we have many experts, each expert can be specific in different type of data. And we can summarize that the MOE model can have a higher model capacity without a huge increase in the computing cost, and it has a better specialization. Different experts can focus on different type of tasks and domain, but it also has some drawback. The first, it is hard to train, and the second thing, it's hard to fine tune. But here's a problem, that is why MOE model is a processing approach. As we shown before, unlike the pruning and quantization, MOE prefers model expressiveness while keeping computation costs in a low standard. And the second advantage is compared to the larger tier, MOE directly scale large language models rather than require train additional student model. And the third advantage is that MOE provide a good balance between scalability and efficiency, making the strong candidate for future larger scale NLP system. And in this And in this paper research three main questions. The first one is how do MOE models compare to traditional dense model in terms of efficiency? Can MOE model achieve the same performance while using less compute? And the second research question is how do MOE model performance across different tasks? Do they work well for both in-domain and out-of-domain data? Are they effective for zero-shot and few-shot training? And the second question is, can MOE model be fine-tuned effectively? Do they generalize well when adopted to specific tasks? What change risks when fine-tune MOE models? And now we have covered the fundamental knowledge behind the large-scale language model and MOE. And let's go to the experiment setup of this paper. In this paper, the author test their approach and compare the MOE model to traditional dense model. In this section, we will cover the model architecture and we will introduce the dense and the MOE model used in the experiment. And we also will introduce the training detail, how the model was trained, including training data set, hyperparameter, and optimization. And last, we will introduce the evaluation method, how the model are evaluated in different tasks. And the goal is to understand how the author conduct their experiment so that we can better analyze their result. So first, in this paper, they use dense model as their baseline. This paper trained traditional dense transform model follow the GPT-3 architecture. In this paper, they train 6 different model with each with such different size of parameter. And the dense model use 4 parameter activity for every token. And for the MOE model, they use 520 experts per MOE layer, but with only the top 2 experts are active per limitation. And by achieving this, the MOE model replace every analytic feed-forward layer in the transformer with the MOE layer. And in this paper, they train 4 different models. Despite have training of parameter, the model are computation efficiency because only a small percent of the parameter are used for token. And for the pre-trained data set, the model was pre-trained on 120 billion token from a combination of 6 data sets like book corpus. It include unpublished books. And the second data set is Wikipedia. They use the cleaned English Wikipedia. And the third is the CC News. It has some it has a lot of English news articles. And the fourth is the open web text. Recreation of the web text data set used for GPT-2. And the fifth is the city story. It is a subset of the common crowd data. And the last data set is English CC100. It is data extract from common crowd. And this data covers both general and domain-specific tasks, making it is a strong benchmark for evaluation generalization. And then let's talk about the optimization at the training setting. for the bench size, they adjust the bench size based on model size, ranging from 128 to 2048 token per bench. And for the learning rate, the learning warm up from 315 million tokens, and the linear and then a linear decay back to zero over remaining training step. And for the training duration, they totally train 300 billion token processed for each model. And for the dropout, 0.1 is only applied to the density model. It is not used in the MOE model. And for the hardware, this model was trained using file SEQ on PyTorch. They use thousands of GPUs, and they utilize fully shared data paradigm training to distribute computation across multiple devices. And also, we need to mention that this paper do not do some MOE specific training adjustment. First is the gradient scale. The expert gradient was rescaled to maintain stability, and also they add a routing loss. An additional loss term was applied to balance expert utilization and prevent certain expert from dominating the training process. And the third, it is the capacity factor, and the expert has a capacity factor 2, which means that each expert can handle twice the average load to avoid overflow. Okay, and to assess the model performance, the author designed experiment cover some mean evaluation criteria. The first one is the perplexity evaluation. It measures how well does the model predict text. And this measure how well a model practice the next token in a sequence, and a lower value maintain a better performance. And the model were evaluated in 2 settings. The first is in domain setting, and the second is out of domain setting. They use which means they use a different data set. And the sets and they also evaluate how the model performance on zero shot and filter shot learning. Can the model generalize without fine tune? The model was tested on 6 NLP benchmark. And also they supervise fine tune this model to evaluate how can the model be adapted to specific tasks. And they fine-tune the model on 8 different classification tasks, and both density and MOE model are fine-tuned to allow the comparison between their adaptability. And to show the effect, to show the MOE is efficiency method, they introduce the MOE efficiency metric to show this measure how much less computer MOE model required to match dense model performance for example, if MOE achieved the same accuracy as dense model, but with 4 times less computer, the speed up factor is 4. And they use the flops, floating point optimers, to show how many computation will used in this um in each task. And so then let's see the result. We can see that in this test, MOE model consistently outperforms dense model at all sites. And for the in-domain task, MOE require 8 times to 16 times less computer to match the dense model. We can see like this. This is how they evaluated. And we can see that in the out of domain, MOE model still still has a measure, still has an edge, sorry. But this still speed up 2 to 4 times. And we can see that at a smaller scale, from 125 million to 6.7 billion parameter, MOE model achieve up to 6 times efficiency gain. And also at the large scale, 16 billion and more, the advantage reduced, but MOE model still provide 2 times improvement. So in this way, we can conclude that MOE achieve better perplexity per flop, means it can match dense model performance while using less computer. And however, this advantage is more expressive in domain setting than the out of domain setting generalization. And then let's go to the zero shot result. It's the left one. Evaluate on 6 NLP benchmark. The key finding can be included that MD model outperforms dense model across all data sets. And that the MOE model achieved the same accuracy as dense model with half the computer. And the largest MOE model significant performance the dense model. But the scaling reduces the efficiency gap, means MOE gain reduced as model grows large. And then for the few shot setting, we can say that the large model benefits more from few shot setting. Dense model shows bigger jump from zero shot to few shot than the MOE model. Even MOE model still performance, but their few shot improvement is smaller than the model than the dense model. And here comes a problem. Why do dense model improve more in few shot learning? This is because that few shot learning rely on generalization across the entire model. Since MOE activate only a small subset of experts, they may lack of the first generation power of a dense model. So we can get the conclusion that MOE is good at zero shot learning due to its efficiency. However, dense model can close the gap in few shot learning as they scale. And let's go to the supervised fine tune. The MOE model will fine tune on the 8 data sets. And the key finding is that dense model fine tune more efficiency in the MOE model. some MOE model actually performs worse after fine tune, and here becomes some problems that why does MOE model struggle with fine tune? This is because fine tune requires updating all parameters for a specific task. Dense model update all layers, but MOE model only update a small subset of export. This limited their ability to adapt to new tasks. This paper also shows some possible solutions for fine-tune MOE model. The first is task-specific export selection, training model to active different export per task. And the second approach is partial fine-tune. Instead of updating all parameters, only fine-tune export layers. And the third possible solution is the hybrid model, combine dense layer with MOE layer for better adaptability. Here's the conclusion that about the supervised fine-tune. While MOE model performs well in pre-trained and zero-shot training, fine-tune require new technical to work efficiency. It is the future work of MOE model. And then let's go further into the MOE speed up factor. The goal is to quantify how much next computer MOE model needs to match the dense model. And we can see that for domain data, the MOE model require up to 16 times less computer. And for out of domain data, the efficiency dropped to 225. And for downstream tasks, efficiency gain based on different data sets. Based on this, we can have some helpful conclusion that the MOE model significantly reduce the training and inference costs. Their advantage is not just in pre-train and zero-shot learning, but reduce in few-shot learning. And we have now gone through the results showing that the MOE model can offer significant computer saving while maintaining high performance in large language model and zero-shot training. However, we also shows that MOE model fit change, particularly in few-shot training and fine-tune. And in this section, we will discuss the advantage of MOE model, why they are promising and for scaling large language model. And then we will talk about limitation and challenge, what needed to improvement in the future. And based on this, we will talk about future research direction. How can we build a better MOE-based model? And the first advantage is the efficient scaling. MOE model enable training of parameter while keeping extra computation costs very low. And they measure performance of dense model, but require 4 times to 6 times less computer. And this makes it feasible to train and deploy larger, more powerful model without very high hardware cost. And the second advantage is the stronger zero-shot performance. MOE shows good performance in zero-shot setting, outperforming dense model at on the same computer budget. And this makes them useful for general purpose AI model that must performance well without text fine-tune. And the third advantage is emerging efficiency. Training dense model is computational expensive and environment costly, but the MOE model reduce energy consuming by only activating a small subset of parameters per input. This could lower the emergent consuming of large language model, makes them more more environment friendly. And the first advantage is specialization of expert. Unlike dense model, MOE allow different expert to specialize in different type of data. It's open a possible model that can adapt dynamic to different tasks or large language model. And then let's go to the limitation and the challenge. The first limitation is limited few short learning gain. While MOE model are stronger in their short learning, they don't improve as much when giving a few example. Dense model benefits more from a few short adaptation, closing the performance gap. And the second limitation is difficulty in fine-tune. MOE model do not fine-tune as well as the dense model. In some cases, fine-tune actually hurts the performance, suggesting MOE require different fine-tune technology. And the third, it is about the training. MOE introduced a routing function which dynamic select export. This adds complexity and can lead to training instability. And the third, it is the increased memory and the latency cost in inference. MOE model require storing many exports, which increase the memory usage. And the routing token to crack the export introduce latency overhead. This make real-time deploy more complex compared to dense model. And then the last part is the future work. The further future work is improve fine-tune method for the MOE, and the second is to build a more robotic export routing mechanism. And the third future work, it is multitask and domain-specific MOE. And the third one, it is to optimize MOE for real-time application. It is corresponding to the limitation we have introduced. And that's all. Thank you.